first square law is basically
I definitely didn't learn.
Got fun, something fun.
I'll just say that.
We're gonna listen to
like formulas for basic formulas, like volume,
a discussion.
area,
Let me pause this.
Surface area.
This is a discussion with Flat Earth Dave and Skylar from Tribune, and they're talking to someone named Joel. So it's quite interesting. So here we go.
Is one of those is what I meant. So 4 pi r squared. And so, all right, so this is kind of what's happening. So imagine these are the different spheres here, right? And so, like you were saying, Dave, the further away you get, so at 1r, one distance away, you have a certain intensity. Then you go 2 times as far away, you have a quarter of the intensity. And then 3 times as far away, you have a ninth, and so on and so forth. It's kind of, it's just a simple. And then this graph here kind of displays that relationship. You've got distance on this x-axis here, and then the intensity here. So you can see 2 times as far away, a quarter, 3 times, 4 times, and so on and so forth. So it gets dimmer, obviously, the further away that you get away. The big important part here to realize is that the further away you get, the less difference there is in brightness. So yes, it gets dimmer, but the amount that it gets dimmer is a lot less the further away you get. So the example I gave here, say you're 10 times as far away, you'd see 100th of the brightness, or 0.01. Whereas if you're only 9 times as far away, you'd see 1/81st, or 0.0123, which is only a difference of 0.0023. It's not that much of a difference if you're 9 times as far away or 10 times as far away. And the further away you get, again, the less difference there's going to be between those brightnesses. Okay, so that's the big point here.
At what distance do we start to really notice that relationship?
Well, that's what I'm saying. That the more distance there is, the less you're going to notice that relationship. So, David, you're muted again. Sorry.
Thank you. That's 2. I'll do it one more time. So you're saying that something is a ridiculous distance, like 100 light years. Long before you get to that 100 light years, you're saying that the difference between 20 light years and 50 light years isn't very much. It isn't as big of a difference as the first few steps. Is that what you're saying?
Exactly.
Okay,
that's correct.
So something's 100 light years away. Then can you see it at 200 light years, or it remains the same intensity at 200 and 300 and 400 light years? It goes to a point where it stops getting less. Is that what you're saying?
Sort of, yeah. So there's not going to be a point where it stops getting less, but because eventually, obviously it's going to be past what you can see. It'll be too dim. So, but there's also nothing obstructing the light from getting to our eyes. Like, for example, in some of the stars in the core of the Milky Way here. Oh, this way. So a lot of these stars here, they kind of just look like a haze at this point, because they're really far. You can't see individual stars with your eyes, but you just sort of see this haze. So the light's still getting there, but you can't make out the stars themselves, the pinpricks, if you will.
Well, the only problem with that, just to interject for a moment, is that normally when you have something that's too far away to see that it's pinpoint, right? When you zoom in on it, you're not going to be able to make it bigger, right? At least not with, not unless you have an intense, a ridiculously intense amount of zoom, right? Most of the time, you would agree that you're not with a camera, right? You're not going to be able to zoom in on something that's 400 light years away. If we're seeing a pinpoint source, right? Would you agree with that? That we're not going to be able to zoom in on that?
To a degree, yeah. Essentially, you can't just get a whole bunch of detail out of something unless you're closer to it. So if you're really far away from something, you can only zoom in so much. So yeah, I agree with that.
Well, it's actually it's not just that, but it's also the actual size of the thing that you're talking about. So there's a point where you're pretty much only seeing a point source of light, and then there's almost no difference between 200 and 400 light years. Is basically the claim that you just made in the simplest terms, right? So if that's the case, then when you have a star that's 400 light years away and you're seeing the pinpoint source, zooming in on it a little bit is not going to bring that size back in, right? It's not going to get larger by zooming in on something that's okay, thank you.
Yeah, that's relatively accurate. Yeah.
Okay. So the problem is that we have tons of videos of people zooming in on stars, and they get bigger every time. So, and that's what P900.
That's a slightly separate subject. Let's go ahead and just finish this off, because the second part of this, I explained the concept, and now I plug the numbers in. Is essentially what's happening here. And then once we get through this, then we can have the discussion. All right. So I said let's try. Let's plug everything in. So there's a couple terms here. So what we were looking at here, when we're looking at like the area, this is like square meters, right? You have a meter here and a meter here, so it's square meters. That's actually going to be called the flux. So that's an astronomy term for it. And then luminosity is whatever the star's wattage is, output. So it's the same thing. The inverse square law is the same thing. We have luminosity here, and we're trying to get the flux. That's basically like if Earth was right here, you want to know how much light is sort of like at this sphere, at that distance away from the star. So that's the flux. So all we need to find is how bright the star is and how far away it is. So its estimated Polaris is 25,000 times brighter and 50 times larger than our sun. All right, these are estimates. But we know the luminosity of the sun is this. So I call it L Sol. So all you have to do is times that by 2,500, because it's 25 times 2,500 brighter. So we multiply that out, we get our luminosity. So this is the supposed wattage output of Polaris. So we have our L. And then here it's 431 light years I put here. You could say 433. It's going to be kind of negligible at this point.
Would you agree that this is all theoretical?
No, I wouldn't. A lot of these are hard numbers. So
which one would you say is the hard number?
Well, certainly the luminosity of the sun.
How did we get the luminosity of the sun?
You can measure it with spectrometers and with light measurements, essentially. Like you can measure how much light is hitting a sensor.
Okay, that's
Joel,
fair.
do you have any examples of anything that's twice as bright as the sun?
I mean, there's plenty of stars. Like stars.
No. When you look at a star, you can theorize that it's whatever number brighter than the sun. But do you have any examples around here of something brighter than the sun? Twice as bright.
The issue with that is the sun is giving off all wavelengths on the electromagnetic spectrum. So I could find something that's brighter in the visible spectrum, but not like on all wavelengths.
I find it hard to imagine something twice as bright as the sun. But let's just go 10 times as bright as the sun. 10 times as bright as the sun.
I don't think there's anything brighter than. I don't think there's anything even visibly brighter on the visible spectrum brighter than.
But let's just say 10 times. Let's just pretend that we can do something 10 times brighter, which is unfathomable to me. And you just carefully, because you're doing some equations. The equations are not empirical evidence. Saying this star is 25,000 times brighter than the sun, and you just roll it off like it's a fact, but you have zero evidence of that, other than it has to be if you pre-assume space is real and stars are far.
Well, I also wanted to get
not necessarily, because there's neutron stars and there's very dim stars as well.
But I wanted a clarification on are we talking about the sun's apparent brightness, like its visual brightness to us, or are we talking about its actual
actual brightness?
Okay, so how did we get that compared to its brightness to us?
We sent probes into it. So I know you don't believe that, but that's how we got that data. That's why it's.
Do you have any evidence of those probes going to the sun?
Yeah, you can look it up. I don't know what their names were.
You can look it up, and it's written by NASA. I believe last time.
I think that was actually a Russian probe. Was the one that went to the sun.
Not Russian, China, Japan, NASA.
You gotta.
We don't have to believe the story about Narnia.
No, you don't. That's what I'm saying. Like, I could say these things happen, but it's kind of hard because I know you guys don't believe it, but that's like, what am I supposed to fall back on, I guess?
But that's kind of where our problem is that we're looking for what we can actually verify, and we're always having to rely on these stories from the accused, right? And so it's just not, it's really not very good optics for the globe model.
All right. Well, let's just continue. We got to find the distance now, right? So we only have 431 light years, but our flux measurement is supposed to be in watts per square meter. Okay, so we can't use light years. So I converted light years to meters, and then 401 light years is this many times that many meters, which are how many is in 1 light year. And so we get the amount of meters. This is how many meters away Polaris is. So now all we do is we plug that in, we get the luminosity of Polaris, and then we get the distance. All I did was plug those in. This is the luminosity and the distance, squared the distance, multiplied it by 4 pi, and then I divided them. And I got this really tiny number, right? So 4.61 times 10 to the negative 9th watts per meter squared, which is really small. That's this many zeros. The sun, for example, is 1,400 watts per square meter. So that's the positives, not the positives. That's past the decimal point. That's 1,400 watts per square meter. This is 0.0000, like really, really small. And so for a comparison, and by the way, the human eye, the lower limit is in the magnitude of 10 to the negative 10. So anything below 10 to the negative 10 our human eye wouldn't be able to pick up. And then another reference is one foot away from your average candle, which is how we get luminosity measurements as a standard. That's going to be 0.01576 watts per meter squared. So it's still pretty small. It's a small, it's a relatively faint light. So then I looked at all of these other stars. So we have Sirius, which is the brightest star in the sky. It's only 9 light years away. And that's still 10 to the negative 8th. And you can see that sort of relationship here of how they're not that different. It's because we have 10 to the negative 8th, negative 8th, negative 8th, and negative 9th. With all these different, Rigel, I never know how to say that, 773 light years away, and that's still negative 8, while Sirius is only 9, and it's still like negative 8. So you have a bunch of different variables in size and intensities. But you have Polaris at 431, and it's only at negative 9, and that's above our limit of being able to see the star. So with all the numbers, with the distance, and with the size, we would be able to see Polaris with the inverse square law. And that's essentially kind of how the numbers would work out. We could now have discussion about the sources of that stuff and all of that good stuff, but with the numbers that we purport to have now, it does work out. It's not against it.
So I'll throw something in, and then Scarlett, you can go. Everything that you're telling us you're great at math, by the way. You're awesome, and great charts and everything. And I could actually show you a chart of an unknown island off of Japan, one of the 7,000 that they just found. And there's an amusement park there with the biggest roller coaster in the world. And I could show you the coordinates for that. I could show you how far it is. I could tell you the specs on the roller coaster, the G-forces. I could show you all of the building plans, everything all about it. And everything will add up no matter how you look at it, sideways, forward, reading it, upside down and backwards. Does that make that amusement park on that island real? Or is it just theoretical? Right? So everything you're talking about is theoretical. You're pre-assuming that space is, infinite and expanding. You're pre-assuming that those lights in the sky are billions of miles away and 25,000 times brighter than the sun, to me, which is absolutely insane.
2,500.
2,500. Well, if it was twice as bright, that's still insane to me. And so this is just a quick quote. All of the theoretical work that has been done since the 1970s has not produced a single successful prediction, says Neil Turk, director of the Perimeter Institute of Theoretical Physics in Waterloo, Canada. That's pretty intense.
Well, what about all the theoretical work done before the 70s?
Like what?
Like general relativity.
I'm not a fan.
That's the big one.
Not a fan.
Yeah, so actually there's a big discussion on upending general relativity amongst even mainstream physicists. It's actually, when you look at that coupled with Big Bang Theory and what they've been teaching in the mainstream schools, there's actually 16 predictions that the theory gets completely wrong. And the James Webb Telescope has actually only apparently furthered the mystery. I know for us, it's like a catch-22. We don't believe in the James Webb Telescope, right? So why are they, spinning these different narratives? I think it's for confusion. But in any case, even if the data is real, right? The data is not lining up for the expectations of general relativity. But again, that's kind of a different topic than the discussion of the stars. When we
my main point was just because a majority of the last interview was saying how the inverse square, we shouldn't be able to see Polaris, and so at least with the numbers that we have, we would be able to.
So I mean, theoretical numbers. You're making a statement that
they're observations.
Hold on, you're not making an observation. You're making a statement. Hold on. That light, the light of a star will get dimmer and dimmer fast, and then it gets less dim and less dim, and then it just travels forever and stays at the same brightness. You have no evidence of that being real, and logically, it doesn't make any sense to me. But you have no way to prove that's real. It's just a theoretical statement that has to exist for your infinite solar system, infinite galaxy, and universe to exist.
I'm not sure that they're infinite. I'm not sure I believe it's infinite.
Well, expanding, very large, bigger than the flat Earth concept, if you will.
Sure, yeah, it's definitely bigger than that.
Right. So you're reaching to places that you can't verify. You can just read books and trust government agencies. They're very trustful entities. And you're not looking here on Earth where we can actually scientifically prove that we're not a globe. I mean, you want to believe that Polaris is 2,500 times brighter than the sun, which that's crazy. I mean, if that was the case, there's other stars that are probably 100,000 times brighter than the sun, or 1,000,000 times brighter, right?
Not a million. I don't think a million.
Okay, yeah, but
many magnitudes, yeah.
But these numbers that you're coming up with, but they all kind of look pretty much the same. And when we zoom in on them, they all
that's proof of the inverse square law to me. I think that's proof of the inverse square law that the further away
they all
things
look the same. Everything just evens out.
Well, in our local celestial neighborhood, yes, but like once you get further out, like out to the middle of the galaxy and stuff, things look a little different. They get denser and they get closer together, and they get into you have nebulae and everything like that. So, and then you have other galaxies, and then you can zoom into and see specific stars in other galaxies.
Do you believe in the James Webb Telescope?
Well, yeah.
Okay, so the James Webb Telescope, it finds a spot called Lagrange Point 2, and that's where the gravity of the sun and moon and the Earth, and it just finds that perfect spot. Okay,
yeah, it's a saddle point. Yeah.
So over the course of 6 months, the sun and the distance between the Earth and the sun change. I had all the numbers before, but as it changes, it would have to move like it's in a tractor beam. Okay, it would have to move, and it's moving like very fast in two different directions. Throughout the year, towards the sun and away from the sun, and you're just believing that tractor gravity is holding it in the perfect spot. Here's my question, though: if you watch the launch, did you watch the launch of the James Webb?
Yeah, I did.
And it was over Earth. Maybe this is that's not it. That's me making a James Webb image. Let me just find something here for a second.
You're good.
Where is it? Here it is. I think this is it. So this is the launch. Let me just see if this is the video I want. And it's up in space. And then is it deploying here? All right. So it's the next one. See, this is it. So here it is, and they're showing us this beautiful curve of Earth. They always show us this beautiful curve of Earth.
At Culver's, this is a Wisconsin-style share a bite kind of dessert.
A couple hundred miles away, right?
Yeah.
Let's round up to 1,000. Let's say it's 1,000 miles away. Got a great shot of Earth. Somehow we can see through all the atmosphere and see the perfect edge of this. And here it goes out here, and it's going to deploy. Let me just jump forward. It's gonna and if you watch, the signal's breaking up here, and it's only 1,000 miles away, probably a lot less. And it's going away. It's already ejected from the rocket.
Yeah.
And I'm going forward, and it's out. It's now putting out its solar panel.
Right.
How does it go park itself 1,000,000 miles away? What gets it to the Lagrange point?
Well, that's literally rocket science, man. I mean, that's orbital mechanics. They exceeded the escape velocity of the orbit, and so it was no longer within the
So you're saying the rocket is in orbit and it pops the satellite out, and then that satellite knows to go 1,000,000 miles away and park itself. Is that what you're saying?
No, not necessarily. It doesn't know to do. It's.
How did it get there? How does it get there?
I think you need to know that it's constantly correcting itself.
How does it correcting? Does it have engines on it?
No, it's got I don't know what the nozzles, pressure nozzles. I don't know what they're called.
So the satellite has pressure nozzles that are pushing against what? What are they pushing against?
You don't have to. It's not the pushing against. It's the fact that it's pushing something of itself out. So it's equal.
And what is it pushing out? What is it pushing out?
Pressure, air pressure.
Gas. It's pushing air out.
Gas. Yeah.
So have you ever seen where we take a vacuum chamber and we put a little rocket and a fan and all sorts of stuff and nothing moves? We just light it and it won't. There's no propulsion. There's no pull. There's no push. We hang a feather in front of a fan and there's nothing. There's nothing. So we could argue that all day. It doesn't matter. Yeah. You're saying that this thing with where are the thrusters on here? If you take a look at it,
I think I can actually see them right there. There's one at every corner. At every corner.
So those four are going to take it out of orbit and park it 1,000,000 miles away. That is a faith. That is a religion.
I have another big question, big one for the
think
thrusters,
it's just math,
right? Well, I'd like to see you try to use math to get out of this one. So we know that there's something called back pressure. That's how all our pressurized systems work when we're dealing with gases, with pumps, right? So we have atmospheric pressure pushing down. Without that, the gas will escape the pumps, right? So out in space, there is no back pressure. So what keeps the gas from escaping?
Gas from what?
The thrusters.
Well, they're nozzles. They open and close.
Yeah, but see, okay.
It's like it's a container. They're contained inside of the thing, and it pushes it out. And it's like if you were to blow in space, I guess.
Space does blow.
It doesn't mean it's just going to deflate immediately.
Can I ask what right here? They're having this bad video feed. Is it going to get better as they get farther away from Earth? Are they going to be able to transmit some high-res pictures because they can't seem to transmit a picture here?
Well, I don't think the craft, the rocket, followed it. So, I'm not sure what you mean.
So the transmitter on the telescope is better than the one that's on the rocket. Is that what you're saying?
Yeah.
I'll go with that. Yeah.
Yeah. Well, I think we could go ahead and move to the next thing I wanted to talk about, unless you guys had something.
No, we'll go to the next thing. Skylar?
I still had one thing on the stars too, because my point on the fact that we can zoom in on all the stars and they all increase in visual size in the camera lens is evidence that they can't be at these varying distances of vast light years away.
So I'm not sure what footage you're talking about.
Amateur footage.
That's not just blurry.
There's hundreds.
Besides blurry.
But you can just call it. I mean, I understand that you can just call it blurry, but even the blur, right? It's getting bigger in size. Like that wouldn't happen. It's a point source of.
So I'd encourage you to take a similar camera, or to ask someone to do this. Take whatever camera that you did that with a star, and do it with like a different type of smaller dim light. Put it off in the distance in a dark area, and zoom into it, and it's going to look the same. Because it's a blurred, it's so exactly how you described earlier.
So
remember how you were
well, when you do it here on Earth, the diameter of it is, or not the diameter, but the actual angular size of it is going to increase, right? Of the actual thing.
No, it's going to get blurry, like he's showing that. That's blurry.
That's blurry. Looks pretty sharp to me.
No, that's what happens when you sort of when your camera zooms in too much, that it's not able to actually process the light appropriately. So all it's getting is just a bunch of random protons.
You can see this with your naked eye. You don't even need to zoom in to see Arcturus. You look at it on a clear night, and you can see this with your naked eye.
Well, yes, it sparkles. It twinkles because of the atmospheric distortion in the way.
The atmospheric distortion.
If another interesting an interesting way you can tell that, and I encourage people to try this as well. look at Arcturus or Sirius or any other bright star when it's lower in the horizon, when it's near the ground, and then look at it again when it's straight overhead, and you'll notice a big difference in the distortion there and the twinkle.
Oh, absolutely! You're looking through the atmosphere; everything's distorted. Look at somebody, a quarter of a mile down the beach, and they're going to be all distorted. Yeah. But you look at something over your head, you're looking through less atmosphere. So just because you can distort things by looking across the thickest part of the air column doesn't mean that's what that doesn't mean anything, actually. But why doesn't this one look like Sirius? Look like Arcturus? This is Sirius. Why doesn't Sirius look like Arcturus? Why does every star have its own personality, focused or not?
That's a really good question, but that's kind of gets a little bit into spectroscopy, because they all have different chemical makes. Obviously, it also depends on the atmospheric conditions of the day, the camera you're using, so that top middle one, for example, is very clearly out of focus.
Absolutely, 100% agree. Let me ask you a question. They tell us that, we're looking at the star, we're looking up through all the layers of our atmosphere and all of the radiation belts and everything else, but we can tell what gas the star is made out of. How come they have never done an experiment here on Earth, like get a garbage can, fill it with whatever gas you want, put it a quarter of a mile down the street, and then get somebody with a spectroscope, the spectroscopy instrument,
spectrometer.
Spectrometer, thank you, and have them tell you what gas is coming out of the can. No one's ever done that.
Well, that's okay. I think that's just because. So what spectroscopy is measuring is actually the wavelengths of light, and the different types of wavelengths of light will indicate different sort of gases.
No, I have a challenge where we get a garbage can with a big bright light in the bottom of it. We fill it with a gas, and then we have somebody with a camera, let's say a mile down the road, half a mile, and they can tell me what gas it is. I'll point the light towards them. I'll pull the top off and let the gas escape with the light behind it. And you think that somebody can do that? It's never been done, right? They haven't tested these instruments here on Earth, and they just shoot them in space and go, that's hydrogen, oxygen, and that's we can tell what that is. It's all, again, theoretical nonsense.
Well, the trash example is just that's not exactly what's happening. So,
well, what you're saying is you could see the light and the gases in front of the light. I'm giving you a light with gases in front of the light. It doesn't have to be a garbage can. It could be a beaker. It could be whatever you want. We can put the gas in a beaker and put a light behind it. And you think you can tell me what gas is in that beaker? So I say you can't.
The thing is, it's heated. It's actual gas fusion. This is an actual active chemical reaction that's happening. That's the thing that's giving off the light. It's not just like a light with gas around it.
Where else do we see that? And where do we see that terrestrially to be able to make that comparison?
Well, it's only with stars. Those are the only stable fusion reactions. Unless you want to blow up an atomic bomb, because that's the one time that we have done fusion.
Let's pretend stars are real and that they're spewing out gases, and then we make a device here on Earth and we can look at it and tell you what it is. How did they adjust it? How did they set it so they can know that it's right? What proof do they have that they're right? What evidence is there that any of it is right?
I'm sorry, Dave. That was just a very general question. I'm not sure I got the.
When they take their instruments here, the spectroscopy. I can't. What's the word?
It's okay. Just spectroscopy.
The instrument itself.
Spectrometer.
Okay. So they're taking that and they're looking at a star in the sky that's burning off gas or whatever, and they can tell what it is. How did they calibrate it? If they never did it here on Earth, they're looking up at theoretical planets and stars, and they're telling you what gases are there. It is all complete and total theoretical science. None of it has been proven.
Not astronomically, we haven't done that astronomically, but we know what types of light and chemicals give certain. We know the characteristics of certain chemicals, and how they fall on a spectrum. That was a close one.
Now you can't say it either. Good.
How they fall on the spectrum, right? So you'd be able to see the spikes in which chemical is what, and that's with most things. You can test that terrestrially, but then when we point it up at a star and we're sort of receiving information from that star, light, electromagnetic information, you can see where the peaks are.
What about all the gases in between that are here in our own atmosphere? It ignores those.
Well, I mean, that's why we have observatories that are actually outside of the Earth's atmosphere and things like that.
Like the self-driving parking James Webb telescope.
Again,
we're back to relying on Narnia.
It's not completely self either. I mean, you're able to calculate pretty almost exactly, essentially, of where it's going to go and how fast and all of that. So it's very.
So you have no idea how it works. You just say somebody knows. The guy in a white lab coat and a bow tie knows.
Oh yeah, I don't know everything, but I know how orbital mechanics work and how things can sort of fall into orbit, fall out of orbit, velocity.
Theoretically.
Well, yeah, but I mean, I got to be honest. If we're just slapping theoretical onto everything,
hold on.
No, we don't have to slap theoretical on things. We have things that are here on Earth that we're trying to measure. That are not theoretical, but go ahead, Skylar.
I was going to say, if you're going to say that, that's kind of a cop-out. We can define what's theoretical and what's, actually verifiable, right? So when we're saying, when you say the hard number is the sun brightness before, right? Again, the thing that made it the hard number was the probe, right? So we had to rely on the story from Narnia. In this case,
that's not the only thing, but that was just one example of one of the many ways we've measured the sun's brightness.
Yes, okay, so I'm not trying to start a whole nother rabbit hole on the sun brightness when we already moved on. In any case, spectroscopy, when we're dealing with a spectrometer, right, there's obviously a big difference between pointing something up at the sky and looking at a light in the sky, right, versus actually having an enclosed environment, a lab, because most of the time when we're doing, from the experts in the field, spectroscopy is done in an enclosed environment. The spectrometer is all enclosed with known variables. So everything's known when they're attempting to analyze these chemicals. So again, we're invoking between millions, billions of miles, trillions of miles, unfathomable distances. We're invoking consistent, unchanging mediums when we have no way to verify that whatsoever.
Well, the verifying is those observations. That is the verification, I guess. So, I mean, I know you guys deny it, but that's the verification, is you can take the same sorts of instruments and measure the same types of things, and you get those observations, then we get these numbers that we work off of.
So Aristophanes, with his sticks and shadows, he measured the length of the second shadow. Hold on a second. And he said, all right, the Earth's diameter is so-and-so. And then later, somebody said, the Earth's diameter is so-and-so, and if we took a stick and a shadow and we put them 5,000 miles or 500 miles apart, those measurements would actually equal the Earth. So you're self-reifying your space with space. You're using space as your proof of space when there's no proof of space.
It's also interesting how confident you are in spectroscopy when, the people at the top actually aren't that confident. They're like, yeah, there's tons of problems. There's tons of things that we're trying to weed out. And a lot of times we do end up with unexplained phenomena. So again, you're just kind of relying on the authorities, right? Because I'm just like you. We were spoon-fed one model. But when you actually talk to the people who are doing the work, people like George Ellis, they admit that there's a range of models that can explain the observations. But cosmology is choosing them based on philosophical grounds.
Yeah, there was a lot there, but we're both sort of appealing to some sort of authority at some point. So,
well, let's stop doing that. Do you have was there a third topic you want to bring up, or can we discuss something else?
I've only got through one so far.
Okay, all right. I thought there was two. Go ahead.
Yeah, so the next one,
then maybe we can interject after that one.
The next one was this video.
One second. I do want to shout out Karen B with the super sticker. Appreciate the shout out and the support. It does help out the channel a ton. Be sure to, if you guys enjoy this kind of content, then definitely check out the GoFundMe. We're trying to make it to Flattoberfest. There's only one way to find out if I'm an AI or not, and that's to get me to Flattoberfest where you have a chance to shake my hand.
That is true. Joel, I don't know if Skylar's real. He could be AI. We're trying to get him to Flattoberfest. You should come to. Where do you live? You should come to Flattoberfest. It's in Las Vegas in October.
Oh, I'm in Ohio, so it's far. If I was closer, maybe. Okay, so let's go ahead and move on to this. I thought this was interesting for you guys to look at. So I'm sure you've seen stuff like this, but I guess the interesting thing of note is the direction that this was taken.
Okay.
So in April, I went to Australia to meet with my fiance, and we went to Kangaroo Island, and this was looking directly south. So I'm curious what sort of explanation that you guys might have for this sort of observation. Because obviously, like on the flat Earth, so this is kind of where I was looking out. That's the way that the angle was with the camera, and we see these stars rotating in a clockwise direction around, I think the rotation point's somewhere around here, right around in there. So that's technically, for me, that would be the celestial South Pole. So if you were to, on a globe, to extend the South Pole out and sort of...
is the Southern Cross in that picture?
Yes, it is. Yeah, it's right there.
Okay.
Yeah. So
Charlie,
the Southern Cross is going around this way.
Yeah, so when you're dealing with the star rotations, first off, just for data's sake, right? Did you happen to have like a compass or any way to verify the direction that you were facing?
Man, there's a bee. Sorry.
What? Yeah. I had a compass. Yeah.
Okay, awesome.
Because we had to use the maps to drive there and we had to navigate there and everything. So, and we just looked out into the. I mean, if I zoomed into this map, this flat Earth map here, I would be standing on this edge of the island, looking this way. So, yeah.
Sure. I mean, the thing is, when it comes to the stars, there's multiple explanations that we can try to explain what's going on there. None of them in any way actually prove the shape of the Earth one way or the other. That's why, as Dave's famous for quoting, shape of the lights in the sky don't indicate the shape of the floor unless you beg the hell out of the question, as the globe does tend to do. So with the observation, I've actually been challenged with 3 points, right? You have somebody on each continent at the same time looking out apparently south, right? So there's a couple of issues. For one, I do understand that you have a map that you can use to navigate locally. However, when it comes to the larger scale, there's also something called magnetic declination. When we actually tried to navigate using a globe back in the 1800s, we were wrong consistently. So we went back and we made all these corrections. And I say we, the British military did. So went out and made all these corrections, and now we have our ever fluctuating magnetic declination map that's almost impossible to predict more than a few years out. What predictions we do have are iffy at best, but we're still going to invoke that maybe we'll have a shift in a couple thousand years. This is actually going to determine how we navigate. However, the stars themselves are not going to be oriented based on the magnetic field, right? So how do we actually verify the direction that you're facing, literally like on the ground versus to the sky? Like, how do we know that you're actually facing south in relation to that map to then have to explain the phenomena?
Well, because I could see where we were through GPS, and you can see on the island, so Kangaroo Island is an island, right? So we had to go out to the island, and it only has certain sides, and we were staying on one side of the island, and so obviously we could see that we were not on the other side, which was toward the north, and we knew that because when we took the ferry over to the island, we came off of a certain part of Australia, out of South Australia near Adelaide, and then we came onto Kangaroo Island, and we went towards to the left, and on either a globe Earth or a flat Earth map, you're still going on to one shore side of.
So long story short, you use GPS, right?
No, because we could see. We drove 10 hours from Geelong, Australia, in Victoria near Melbourne, all the way over to South Australia.
If the circle was like 5 miles in diameter, you wouldn't even realize that you're making a big circle, right? That's why people get lost in the desert constantly. So I mean, to say that you know definitively the orientation that you are, based on like something like the GPS, or that we were just traveling and it didn't feel like we were turning left or right. That's not very definitive, right?
Well, there was no inaccuracies. I mean, there was nothing to say that we were wrong, and we never.
Well, if it was backwards, let's just for a moment, and I know that we're going into conspiracy land, right? We make no bones about it. There's a conspiracy, right? If there was a conspiracy and we're dealing with something that is a projection from reality, I mean, why wouldn't they make it accurate, right? People would figure it out immediately if the maps weren't adding up. But I would add that people actually aren't navigating using a globe Earth, right? They're actually navigating using flat maps. Most commonly, the Mercator projection, 99% of maps are flat. There's only one map that's not, and that's a globe. And it's not even really used for navigation, right? When it was, it failed, and they had to invoke a changing magnetic field.
Okay, but this is kind of hard to discuss, because I feel like it's so like point blank. Like even if the maps were distorted or the GPS got me to the wrong location, I was still on a certain, like I could see the coast. I was on the beaches, and you could see the consistency with that, with satellite imagery, with GPS, with maps, with compass. I mean, it was all, there's nothing wrong with it, I guess.
Joel, so first, compass, when navigators are using compasses, they're in the south, the farther south they are, the more out of sync they are. They find themselves 20, 30 miles a day off, according to their compass. So what NASA has done is they've taken all those data points and they've programmed them into GPS. Anybody can use GPS, but nobody is allowed to see the source code, because if we saw the source code, we'd say, whoa, why are they making all these adjustments? So you have no idea what direction you're facing down there, but let's pretend you are facing south. That we don't even know if the southern stars are a reflection of the northern stars. We don't know what they are. We don't know what stars are. We don't know anything about them, and their motions have nothing to do with the ground that we stand on. Can you admit, if we're on a ball, that there's physical curvature?
Yes.
Okay. So if I'm on and wherever you are, let's just say it's the top of the ball. Okay. So I'm here on an airplane, and I'm looking at it's a perfectly clear day. I'm on the runway, and I can see stars on the horizon. So I'm looking this way, and I see stars right on the horizon. Right.
Yeah. Right.
So I'm in Germany, and I'm going to fly to Brazil. So I'm flying down over the ball, and when I get down here, those stars that were on the horizon are now over my head, right?
Well, it depends. It depends, like how much the Earth is rotated in that point. But yeah.
Well, the Earth is rotating this way, not this way. So I'm going from the north, right? The stars on the horizon. If I stayed there, and the Earth is rotating, those stars are going to stay there. If I go down, those stars should be on the top. So I want to show you a video that a pilot gave to us. And this is from Germany to Brazil. And it's a time lapse. And if you look at the stars, they're not rising up. You would think that they would rise up, but they're just, the only time they move.
Yeah, that's an awesome example of him going along with the Earth's rotation.
No. So this is what Google Earth says that flight should look like. Right?
Yeah,
Google Earth says
Google Earth isn't rotating, actually.
It doesn't matter.
To the chat, if you think it's a globe, you need to dig deeper because you're believing a huge lie.
Rotation, the east-west rotation has nothing to do with north-south navigation. The stars, as he's diving over the Earth, these stars should go up. So this is reality versus Google Earth that is simulating what we're supposed to see on a ball. There's a problem. There's a big problem there. This is what it should be. These stars should just be rising up as you're diving over the ball. Whether it's spinning or not spinning has zero.
Dave,
if you were flying east or west on the equator and you had something on the horizon, yeah, you're flying towards it. It's going to go up or down slower, but north-south has nothing to do with the spin of the Earth.
Wait, you said he's going from north to south? Are you saying he's going to north to south in that?
Yep. North to south. Yep.
Yeah, that's why you see the stars rotating this way.
Where was he flying from?
From Germany to Brazil, I believe, or somewhere. Germany, for somewhere down there, down below the equator.
Okay. trying to think.
And you can think. Here's one. Think about it, and maybe not.
I just think, Dave, that the answer is the Earth's rotation, and so to say that has nothing to do with it, that's just dismissing the main reason that would happen.
Well, let's look at the Earth's rotation. You got a plane here in the north. Let's call that Germany, and they want to fly here. Okay, right? But the Earth is spinning, and by the time he gets here is now over here. So he has a choice. He could kind of keep correcting to the left, and chase it all the way over. Or he could say, you know what? I want to go here, so I'm going to fly this way because by the time I get there, here will be there. Okay? No one ever does that. Airplanes pick their location. They say it's that way, and they head in a straight line and go that way directly to the location. Okay? If the Earth was spinning, you got a problem, right? But the spin of the Earth, you gotta model it out. The spin of the Earth, east and west, have nothing to do with that observation.
Yeah, let me show you guys something. All right, so before you dog on this program, I need to tell you that it's extremely reliable because I've used it most nights.
Goes off of azimuth measurements.
Well, no, it does have an azimuthal grid, but no, it doesn't just purely go off of azimuthal. So this is close to where I was in Australia, so you can kind of see the same thing that was in the video.
Was the ground curved like that where you were? Did it swoop up like that?
No, obviously, like if you zoom out all the way, like it's going to be, it's just a matter of point of view. So really, it was probably closer to something like this. Because it was a wide-angle lens, but otherwise, the reason I had to do that because otherwise you couldn't see enough of the screen. But the point is, this is looking directly south. That's right towards the South Pole, and I want you guys to notice the specific stars that we have here. We have the LMC, which is the Large Magellanic Cloud. We have the SMC, the Small Magellanic Cloud, and in terms of the Milky Way, you have the core there, and then up here you've got where's Polaris? There's Polaris. There's a crux.
So we're not even really looking at the sky here.
No, but if you went to the same location and looked up, this is exactly what you would see. So this is a reliable software program or software.
So let me just before you finish that point. If I put you in a planetarium and it showed you those same stars in the same locations, would that mean anything?
Well,
would that mean the Earth is a globe?
Well, so sort of, because
so the planetarium proves the Earth is a globe because you're on a floor in a planetarium. You're looking at lights in the sky that are 50 feet away from you, and you think they're trillions of light years. Go ahead.
Dave, I need you to be charitable with me here a little bit because what I'm saying is, if what you see in the planetarium is the exact same thing as what you see in real life, then it's reliable. It's not just because you see it in the planetarium. Okay, this is just what I can use because obviously I can't take you guys outside to look up. But this is, so in the southern hemisphere, that's the southern celestial pole right there. So all the stars, you're on the bottom of the globe in Australia, and you're looking down towards the downwards from the Earth, from a right side up Earth anyway. And then here we have where I am, and you can see totally different stars. You can see, so this is the literal opposite side of the Milky Way because the other part was down here. You were looking through there. So this is what I see every night where I live, and they're actually rotating counterclockwise around a different point. These are different. You didn't see Cassiopeia. You don't see M31. You don't see, the Big Dipper. You don't see Ursa Minor. You don't see any of these. And this is looking directly north, right? Because that's the North Star. And all of the stars rotate around the North Star. So you have the southern hemisphere where it rotates counterclockwise. And we have all of these constellations. They're beautiful and whatnot. I'm sure we could all agree with that. But they're totally different stars than are over here. Totally different.
I think what Quinlivan and Hughes does really well with clients is we try to avoid surprises. And what that means is letting the clients know what they can expect in their representation, what they can expect with maybe the questions that they have and how they're going to be answered or dealt with. and just keeping those open lines of communication. I think it's important, and I think everyone at Quinlivan and Hughes understands that it's important to communicate with our clients in such a way that we know that they understand, that they feel like they can ask questions, and that they're going to get the answers that maybe they don't always want, but the answers that they need.
Try Tide Power Pods with 85% more Tide in every pod.
Who needs that much more Tide? He does.
No, what does that mean?
It means you're gonna need more Tide. See? More likes, more Tide. The more adorable, more Tide. Everyone's gonna need more Tide. You're gonna need more Tide.
It's a mess out there. That's why there's 85% more Tide in every Power Pod.
An actual thing. Like, do things get displaced in relation to the viewer based on how far they are in their relative position, right? So in other words, even if we're dealing with a flat plane, right, if something is moving level parallel overhead optically to the observer, would it not appear to drop? Or would it still appear to drop because of perspective?
Like in terms of something getting further away from you, that's like has a certain height, and the further away you get, sort of like looks like it's
two parallel planes.
Yeah. You can see that with train tracks. Sure. Yeah, the distance.
So what if the stars were close and local, and you're flying underneath a low sky? You would see stars curving over you as you go by. They would drop down lower. They'd be high above the plane as you're flying, right? And the reason that you see different stars is simply because the stars are so close. If you and I were in a room with 10-foot high ceilings, and there's recessed lighting, and they're in all different patterns. Look, there's a starfish, and there's a bull, and there's a cow. And I say, hey, Joel, walk 5 miles. We're going to expand the room to 10 miles wide. You go 5 miles down, walk there. So I wait, a little while, and I can't see you anymore because my vision has brought the ceiling to the floor, and you are too small for me to see. So I call and I yell, and my voice spreads out like light spreads out, and you can't hear me. So I call you on your cell phone, and I say, Joel, are there still lights above your head? You'd be like, yeah. I see a horse and a dog, and I'm like, well, what happened to the cow and the bull? Well, I can't see those. Okay, you can't see the stars that I'm under. I can't see the stars that you're under, and we're just 5 miles apart with in a small room with no atmosphere causing issues, just perspective. So that's why you can't see the same stars from the south, because they're too far away. Problem is, on a globe Earth, there's a physical horizon. So on a globe Earth, if you use globe math, you love math, there's a certain distance, which is the max distance you can see. Never, ever can you see farther. Only if conditions like waves on the water or density of the air, could you see less. You can never see farther because there's a physical horizon. On a flat Earth, our horizon is very optical. And depending on weather conditions, we can see farther than we should be able to see. So, a 6 foot tall person standing at the edge of perfectly calm water on a perfectly calm day, a perfectly clear day, should only be able to see the surface of the water for 3 miles, according to your math. Okay, there's a 6 foot drop in 3 miles, according to the Pythagorean theorem. Okay, so I should be able to see the surface of the water, but we can see the surface of the water for magnitudes farther than that. We can see things magnitudes farther, right? But globers like to say, well, I can't see that mountain. Therefore the Earth is a globe. And then we break out a infrared lens, and all of a sudden we're like, oh, we can see that mountain with infrared. And the only thing they have is screaming refraction, but infrared even cuts down refraction, right? Without an infrared, you see a blue sky, right? But we can see this mountain with infrared. And infrared, if it's refracted up, it should be even less. But we can see all of this mountain except the lower part because the atmospheric density. So we can see too far because the horizon is a theoretical limit of your vision, okay? It's not a physical horizon.
Yeah, but what about the rotation? Because that's specifically the
rotation?
So the rotation of
Yeah, so the rotation is so this is something that I've actually been trying to send you something, Dave, for the background, because I can't share my screen while I'm streaming. Otherwise, I'd pull up the visual for you. But we actually
where are you sending it?
Well, no, it's just too big to send. So I was trying to send it in my email, but it doesn't work. But anyway, in any case, Walter Bislin actually did us a favor on this and actually modeled out what the stars would kind of look like on a flat plane. They did use arbitrary stars, so it's not like you can see specific constellations or anything like that, but it basically just shows the general position of where the stars were and then what it appears to be optically to the observer. The reason why this happens is there's a huge discrepancy or a miscommunication in what we're actually dealing with. So we're dealing with measurements in our visual field. Right, we're dealing with things that are very far away, and there's a big assumption that everything is in Euclidean geometry. We assume this because for a lot of things it tends to work. But if you Google it right now and you look up the geometry for visual space, you'll actually see that there's not a set model for it. So, oh, good. They've got it pulled up right there. Perfect. So there's actually not a set model for what the geometry we should expect to see in visual space is. And there is now evidence coming out that we are seeing a hyperbolic geometry as our visual space. In other words, spherical geometry. There's something known as the Alley experiment. There's a paper that is referenced that I also sent Dave a quote from. Then this would explain the spherical nature of what we're seeing. As far as the rotation goes, it's an optical phenomenon. So it's literally an optical phenomenon. You would have an optical convergence point at the furthest point away from the center point of rotation. Because again, the further out that things get, the more they're going to tend to converge. So the things that are rotating above you are obviously going to, if you're over the equator, actually, it's going to appear more straight. And then as you get further away, it's going to optically converge again as you look out. So this is just one of the explanations. Another explanation is that there's literally 4 different optical rotations, which is very possible if you just think of it as like gears, right? You have one rotation in the center and then 4 opposite parts of rotation coming off of that. So, but before I even attempt to explain any of that and get into the bottom of what's happening, I like to start with first principles, which is why I had asked you, how do we even verify the general position of where we're looking definitively, right? There's the quote right there. Euclidean geometry widely accepted as the model for our physical space. However, there's not a consistent model. There is evidence that our eyes work to make pictures and images of the physical space using a hyperbolic model. And this is obviously what we're basing our measurements off of. So I'm wondering what you would say to that. And if this is true, where is this accounted for in the mathematics that you present?
Well, there was a lot there. I got some stuff down. It certainly wasn't any simple sort of message that you just gave there. So you're talking about non-Euclidean geometry.
Right.
Okay. And how that relates to our sort of more hyperbolic perception. But you mentioned how, so for example, if you're on the equator and you're on a globe, you would expect the sort of the stars in the sky to sort of barrel over from you have the north here, the south here, they barrel over you just the same way. If you turn it right side up and you're on the North Pole, the stars would just rotate around that top point. If you're in the South Pole in Antarctica, you look up, it would be the same thing, but with different stars. So, but my question is, what about the different stars? I mean, they're completely different, and you can watch as you traverse the globe, the different stars. So
that issue was actually solved before the rotation issue was even solved, right? So what happens is, because our visual space is curved, the things that are further away are obviously going to be dipping down. So what ends up happening is these stars, the stars that are over, let's say, the northern hemisphere, as you drift over the equator, you're going to start to see both of them, because again, the closer you get to something, the more it's going to rise up to your perspective. The further away, the more something's going to fall. So as you move away from the northern hemisphere, those stars are going to fall to the horizon and become invisible to you. And then the stars that were invisible to you, that you moved closer to, are now going to be visible to you. Long story short, let's pretend you're in a big warehouse with lights over top. You're simply underneath one set of lights.
Yeah. You're 5 miles away in the same room. We look up, we see the different stars. Now, as you walk towards me, you can't see the stars that you left behind, and you start to see the stars that I'm seeing. You're on the north side of the room, on the south side of the room. Okay, it's the same thing. What's that?
How low are these stars to be?
We don't know. We don't claim. But I know a little bit. They're 25 trillion miles away. I just made that up, right? But your theoretical, ideas of where the stars are scientifically impossible, if you ask me. Our stars are very close. I don't know how far they are, but I don't think they're thousands of miles away or millions of miles away. I don't know. I'm not going to make a claim.
Well,
I like looking at things here on Earth that we can actually measure.
This is just a question. I'm saying, so if you were to measure and work out the math of how far something would have to be to go a certain distance away from it to where it looks like it goes down.
Well, here's the problem.
You've seen mathematically.
Well, you've seen the orthographic view of the flat earthers say the sun's 3,000 miles up, and with the size that they say the earth is, the sun would never set. Well, I don't think it's 3,000 miles up, but even if it was, they're not taking into effect that somebody standing under it, it's directly above them at X height. And now somebody farther away, it doesn't stay at X height. It gets lower already just due to perspective. And they go farther away, it appears lower and lower. Okay? Phuket Word, you don't know who he is, but he recently did a video on it, and it's really it's how perspective works. People don't teach perspective in school, because if they did, people would be like, wait a minute, this doesn't work out. We don't live on a crazy globe. I want to get back to, you're talking about seeing the stars and stuff. The stars, we can't prove what they are. We don't know what gases they are. We don't know how far they are. The brightness is 2,500 times brighter than the sun. That's a made-up story.
Well, that's only one star, though. There's different ones that have different.
If you told me something was 1.5 times as bright as the sun, I'd have a hard time believing it. Okay, because the sun, because no, you have no examples of anything brighter than the sun. Let's say, they could do something in a lab, and they say it's 10,000 times brighter than the sun. Show me something twice as bright as the sun. They've never ever done it. But instead of looking up at these lights in the sky, let's just come back down to Earth for a minute. You said earlier, you agree there's a physical horizon. You agree that there is curvature of the Earth. Do you know anyone in history, or have you ever measured the curve of the Earth?
To the second question, no. To the first, I would say yes. But
like who? Well, and the other one is axial rotation. Do you know anyone in history that measured axial rotation, and can you tell me how?
Axial rotation? What do you mean by that? Like
the Earth spinning on an axis. The Earth spins on an axis.
What do you mean measure that?
How do you prove the Earth is spinning without looking at the lights in the sky?
What do you think would be a satisfactory answer for you?
The Earth isn't spinning.
No. I meant to test it. If we were to have a test of that, it's rotating.
If the Earth was spinning or curved, you'd be able to measure curvature. So let's look at this. Okay. So when you're down low, the thickest part of the atmosphere, you can't see 100 miles. Okay, because the atmosphere just becomes too thick. Right. But the higher up you are, the air is thinner, clear, less pollution, less moisture, and you can see farther. Here's an observation from a mountaintop.
Oh, yeah, I watched that video. Yeah.
You watched it. So what is your explanation on why we can see these mountains? We can see all of them in the right places and everything. The tops of these mountains should be over 40 miles below the curve. Now you can say, well, the curvature calculator is wrong. It's a parabola. You can say whatever you want. Oh, it's the hump. It's the Sagitta. Okay, only 20 miles. The tops of these mountains, which is nonsense, should be 20 miles below the curve, but we can see them. What is your answer for that other than refraction?
I'd have to look into that. I can't just.
You know what? You would be the first one with a scientific belief system that is willing to look at it, because mainstream science won't look into it. No one will look into it. Okay.
Yeah, I mean, I could look. I got that down for next time. Then
there you go. Come up with an explanation on how we can see all of these mountaintops.
Okay. Yeah, I will.
All right. Beautiful.
I like how you assume on faith that the curvature calculations are just going to work out. It's not going to work out.
I never said I'm good. Okay. But Skylar, you've got to like give me. I mean, how would you work it out then? I guess like
there's an Earth curvature calculator, right? So I would simply find the height of the mountains, right? I'd get the distance of the observer here, 700 miles, the height, and then I would plug those numbers into probably the Walter Bislin Earth curvature calculator, and then I would invoke standard refraction just to be a good sport, right? And then I would see what figures it give me, and then I would compare it. When you do compare it, it says that there's like 80 miles of curvature that's supposed to be there. Those mountains are not 80 miles high. So these are the things that to us, seem to falsify the model that everybody just keeps insisting on with hypothetical, celestial proof.
Well, I think celestial is strong because again, if we are on a globe in space, you should be able to look away from it and be able to tell and be able to predict what you would see. But is what I'm saying. But
the whole thing with the assumption of Euclidean geometry being shattered doesn't shift or make you want to relook into way that we're doing.
I don't think it's shattered. I mean, obviously they just said there's alternatives and there's different like ways to mathematics, like the difference between radial.
No, well, so when I say shattered, right? I mean, I don't know how it could get more shattered than well, they nicely did it, right? They said the assumption of Euclidean space is wrong, and we have evidence that we are building our space in hyperbolic geometry. So I'm not sure how we wouldn't consider that shattered.
I actually think that's actually referring to like math, like tensor calculus and like general relativity, because that's using Euclidean geometry, and they were sort of criticizing.
So this all was done as a result of the Alley experiments, were terrestrial experiments, right? So we're not dealing. When they did this observation, they weren't even using celestial observations, right? So this can happen in the small scale, which is, again, this is the kind of stuff that we like to go on when you say that, well, yeah, both sides are taking something on faith. Kind of. At least our side, we have the ability to go and verify the terrestrial examples, whereas your side, we have to take on faith that this entity, NASA, started by Project Paperclip, Nazis admittedly, sent probes out and gave us back the correct data.
Yeah, I mean, but I guess, because then I just ask, like, and, then, like, what is this thing? What is this? And then what are these?
Well, could you accept that we don't know, and that maybe the people claiming to know are just trying to get a leg up of credibility? Or that maybe you've been misled information-wise, and that the people who are actually doing the work on the ground don't claim to know these things, right? They claim that this is a theory that could explain the phenomena, but it's a work in progress, and it's surface level at best, right? It doesn't even begin to explain the deeper phenomena. Like, you can't explain what gravity is. You can't explain quantum mechanics.
We can see other galaxies, though, is what I'm saying.
Joel, you see lights in the sky that somebody told you is another galaxy.
No. You can see the shape. Like, you can see
a shape that somebody
itself.
told you is another. Like, did you take that picture behind you? Where's that picture from?
Yeah, I got it. Yes, I took this picture.
You took that with your camera?
With my GoPro, yeah, right here.
Your GoPro took that picture of the sky?
Yes.
That's a great picture. Good job.
Thank you.
You're taking pictures of lights in the sky that are not hundreds of trillions of miles away. They're close. They're close. But to assume that, that's a disc shape and it's kind of fuzzy, therefore it's 100 billion stars with 1 trillion planets, right? To believe that's just a belief, right? So here's the example I'm looking for, okay? Is this the sun or the moon?
I can't tell. Probably the moon.
Is it a sphere? I
also can't tell.
Okay, that's right. And guess what? It's only about 1/4 mile away. And as we bring it closer, you see that it's a train and it's not even a sphere. Okay? It's got rectangular lights on it, right? It's got orange lights. It's got different color lights. But you saw a sphere at 1/4 mile away. But you think that you can see a light in the sky 100 trillion light years away and tell me what it is? You couldn't even tell that this is a train with 8 different colored lights of different shapes that are not even touching each other. It looks like a sphere. It's how we see.
But what about things that are shaped like what we call galaxies?
They're shaped like what we call, you know what? An egg is shaped like a galaxy. I don't think there's 100 trillion stars in my fried egg in the morning. Okay? It's shaped like a galaxy. It should be. It should have 100 trillion stars in it, and it should be amazing. I bet if I took a really close-up picture of it, I could send it to NASA, and they'd be like, wow, you discovered a new galaxy.
Yeah, I mean, okay. I don't know.
I'll take an okay. I'll take an okay. That's all you need. That's all you need to give me.
Yeah, I just, I wouldn't really know how to respond to that.
But here, I think I made a good point. You couldn't tell what shape this was, what it was, or anything at a quarter of a mile away. You think that you can tell what something that looks like? They say, hey, a galaxy is this shape. Okay, you think that you can tell what that is? You were told what it is, and therefore anything that's that shape, you believe it because that's what you were told. There's zero evidence for anything that you have brought up today. It is all theoretical. Getting back to the spectroscopy experiment, I want someone to do a I can't say the word, spectroscopy experiment. You get a vial, we should be able to get a beaker full of whatever gas, put a bright light behind it, set it on fire, whatever you want, and somebody a quarter of a mile away we should be able to tell them what it is.
That's not how spectroscopy works, though. That's not.
How does it work? we already went over this. But
we already went over that. But
okay,
so let me just one more example, and then we can start
go for it.
Shutting it off. But so this is the same program. I've seen these things myself, so I'm not like just showing you gibberish that I haven't seen myself. First of all, I'm sure you've heard the Andromeda Galaxy. That's our nearest galaxy. It's quite large. It's huge. I've seen it. You can see the shape.
I can make that in Canva right now.
What's that?
I said I can make that in Canva right now.
Yeah, but I'm not. You can't say this is fake, Skylar. This is real. I've seen it. This isn't like some made up. We have pictures of it. You can go outside with a telescope right now with a DSLR camera, put a star tracker on this, and take a picture of it. So this isn't like some just made up thing.
You said that we could put a star tracker
in the sky.
How is it that we're keeping up with this other galaxy, right? That's definitely not within our galaxy. And when we're whipping through space over 1 million miles per second.
Well, because space is really big. So here's another one. So here's the Whirlpool Galaxy. I've seen this one too. You can see the shape. You can see this smaller galaxy here. It looks like it's kind of sucking it in. It's really cool. And then here's another one that I've seen, the Triangulum Galaxy.
Skylar, what if there was a book that said that these are spiraling lights that were just a couple hundred miles away? And that's what you were taught. Now, if I showed you all these and told you that there were galaxies trillions of miles away with hundreds of billions of stars that are bigger than... But my point is, you could defend either one of them with an equal amount of evidence, which is zero.
I'm saying... So
try not to do a spit take.
It's sort of like what you're calling it. It's just a matter of like semantics of what you want to say that it is. And then, of course, this would be our galaxy that we're inside of, so we're inside, that's the center of it. And you can kind of look away from it. So this is our Milky Way, obviously, and any of us could see that.
It's not obvious because you were told that. You're pre-assuming.
No. I'm saying that this is all stuff that you can go out and see yourself, and that you can take pictures of.
But you couldn't tell what a train light was, right? It's a cool story, bro. It's a cool story. So you have zero proof of it. You were told that it's a galaxy. You were told that it's trillions of miles away. You were told it's 2,000, or you figured out on your own that it has to be 2,500 times brighter than the sun. These are all things that you have zero evidence of. Zero.
But wouldn't the evidence be the observation, like looking at it?
The observation. But as I said before, if you were taught in school that these galaxies were actually energetic sources of spiraling light that are, a couple hundred miles away, that would be your story.
Oh, hey,
and then
there's
another one.
There was something. One of the biggest debates in astronomy was actually this exact point, when we believed that the Milky Way was the entire universe, and we didn't believe there was other galaxies. We didn't even know what a galaxy was, and so where'd he go?
I'm still here.
I'm here.
Back.
Okay. So the point was it was called the Great Debate. You can look it up, where it was Andromeda, that first one that I showed you. they were saying, oh, that's actually not a nebula. They thought it was a nebula. And turns out, well, Hubble discovered that it was a galaxy, and you could look up how he did that. But
so they changed their story. They literally just changed their story.
Well, I think it would better term would be updated their story, but
that would be impossible to catch them in any kind of right. How can you falsify the model if you're just going to change it whenever you get narrowed down?
It wasn't falsified. It was added because they didn't deny that the Milky Way existed. They just said
kind of like refraction. Kind of like refraction was added to save Earth curvature.
Well, you and I both know that refraction is a thing. Like, you can see how refraction works.
So refraction never brings anything up that's gone. It can move things that are in your visual range, but it doesn't bring things back from when they're completely hidden and keep them there over 24 hours.
I'm just saying refraction itself is a thing.
Refraction, but that doesn't explain the observations. For example, the famous shot across Lake Michigan of Chicago, there's a time lapse, 24 hours with different weather coming through day and night, and the buildings never move 1 inch. They're just there the whole time. And we proved that they're not refraction because a couple of our guys got in a boat and watched it and went across the lake, and it should have disappeared at one point because they're getting closer to it. The refraction should change, and it never changed. We proved that it's not refraction.
All I'm saying is, with the great debate, it wasn't falsified and debunked. It was just added onto. They're like, oh, I guess the universe is way bigger than we thought it was.
Well, that again, theoretical nonsense. You believe that this is a giant star manufacturing factory where there's dust and gas in space. Another scientific impossibility that is collapsing upon itself and spitting out stars like ping pong balls. Okay, that's what you believe, right? This is a nebula that produces stars.
Yeah, it's the pillars of creation. Yeah.
So cool story, bro. It's a cool story. It's not even a cool story. It's ridiculous. Okay, how do you have gas and dust in space?
Well, I think we probably won't get into that topic here. But
when you say things like, my issue is when you say things like, well, the observations are the evidence, right? Do you know that we changed the distance to the sun over 7 times in modern history?
Yeah, probably. We updated it. I think we got more refined.
Do you know why that's significant? Yeah. Do you know how much they changed it by, first off? Do you know how much they changed it from?
No.
1,000 miles was the first predicted distance. So they have...
Who did that?
I can't remember the exact names of everybody who did the predictions. But in any case, we end up now, obviously, with our figure of 93 million miles. You admitted yourself that, they probably changed it to update it, right? So here's the issue. We base a very important unit of measuring all these other distances off of our perceived distance to the sun, which was the astronomical unit. It's also how we defined our speed of light, right? We simply define it as constant. We think that the sun is so far, and then we measure differences in angle. So it's pretty funny that we don't actually have in my opinion, a real measurement, a direct measurement of light. It's an inferred measurement. But in any case, the AU was changed 7 times, which means that the units to all the other stars were changed several times. And now, this point was kind of breezed over when Dave brought it up. The North Star, they're talking about give or take, right? That means they could give it 100 million or 100 more
light years.
Yeah, 100 more light years, or take 100 light years away. That's a 200 light year discrepancy. And we're going to sit here and pretend that that's not going to have anything to do with the other predicted distances, when we know that several other predictions were made about the distances to other galaxies and other stars based on where our projected distance of the North Star was. It's a house of cards.
Joel, the mainstream science, if you don't agree with them, you don't get published. So mainstream science tells us it's 93 million miles away. But during one of the recent solar eclipses, a bunch of truthful, honest, researching amateur astronomers said, hey, they did the math and there's something wrong. The eclipse doesn't work. The sun has to be farther. And I forget the number, but it was significantly farther. And so all of these chat groups, these articles started popping up, and then they all disappeared. Inside of a couple days, bam, you can't find any of them. It was completely squashed off the internet. And well, wait a minute. There's something wrong with the eclipse and the shadows and everything. It didn't line up, and that was just squashed, and nobody heard about it.
At Domino's, order carryout online or by phone and get any one-topping pizza for $7.99 each.
Again, this is why I say it's theoretical at best. I'm not saying that the theory can't work, right? It very well could, but we can acknowledge that the observations on their face are not proof of themselves. In fact, you even stating that is a literal begging the question, or also known as a reification logical fallacy. If an argument is logically...
All right, you guys are going to hate me. I got to turn it off. I have to use my phone, and I might come back out when it gets a little darker out. Thanks for hanging out. We will see you later. Make sure to follow.